Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoyed this digital production created for alumni and friends like you.
Welcome, everyone. I am Tamara Ledley, and I am going to be facilitating this climate solutions workshop today. I'm first going to introduce myself a bit. I am an MIT alum. I received my PhD from MIT in atmospheric science and climate science, and did my dissertation on modeling global climate change, basically looking at ice age cycles at the time. I transitioned my career from doing climate science research after about 15 years to climate science and earth system science education, and spent most of my career involved in teacher professional development and curriculum development for students to help teachers teach about climate change more effectively in their classrooms. I also now am an adjunct professor at Bentley University, teaching global climate change to undergraduate business students. So a lot of what I do is to try to bridge various kinds of professional disciplines to help people integrate understanding climate change into the decisions that they make for their companies, their organizations, and their communities. I also facilitate quite a few of these climate solutions workshops. So we're going to be using this model En-ROADS today. En-ROADS stands for Energy Rapid Overview and Decision Support Model. It was developed by Climate Interactive, a nonprofit in collaboration with MIT Sustainability Initiative. So we're going to do a little bit of an introduction on the background of climate science. And then we're going to explore scenarios of success. And so I'm going to first demonstrate how the model works, and then you in breakout rooms are going to get the opportunity to explore the different solutions that can be implemented to address climate change. And what we're going to try to do collectively is when you come back from the breakout rooms, you'll bring the top solutions that you have identified. And we're going to collectively try to reach the goal of having temperatures increase no more than 2 degrees Celsius by the year 2100. And then we'll have a debrief. So first, an introduction. Let's briefly review the science and what's at stake here. So this is a graph of the atmospheric carbon dioxide over the past 800,000 years. This horizontal graph here starts at the present here is on the right-hand side, and present is defined as 1950, and it goes back 800,000 years. The vertical scale is the carbon dioxide concentration in parts per million, and the range over the last 800,000 years before 1950 was a low of 170 parts per million, about 675,000 years ago here. And a high of about 300 parts per million, about 325,000 years ago here. But as you can see on this time scale, the graph goes straight up from there. And the current levels are on the order of 418 to 19 parts per million. So where did all of this carbon dioxide come from? So this scale here goes from 1850, basically pre-industrial times, to the present. Again, the vertical axis here is carbon dioxide emissions in gigatons of carbon dioxide per year. Back in 1850, most of those emissions were land use changes, mostly the clearing of land for basically farmland, agricultural crops. And you can see that there has been continued emissions over time from land use changes. It's gone up and down, but pretty much has not grown significantly. Then we see here in the late 1800s, coal became a significant source of energy, emitting carbon dioxide, and has grown ever since then. In the early 1900s, oil became a significant source of energy and began to grow also. And so you can see this black wedge has gotten a significant, has had a significant amount of input of carbon dioxide into the atmosphere. And then we have around 1950 here, natural gas became another significant input of carbon dioxide into the atmosphere. These others here are emissions from cement production and gas flaring. And so that has, while not as big as the others, the other fossil fuels, it also emits a good amount of carbon dioxide into the atmosphere. But carbon dioxide, as most of you probably know, is not the only greenhouse gas. So this is a graph of the total annual global greenhouse gas emissions by gas. And so you can see here that the carbon dioxide from fossil fuels that was on the previous graph is 68% of all of the emissions of greenhouse gases. The CO2 from land use changes and forestry is about 7%. But then we also have methane here, which is 18%. And that comes from agricultural practices and from industry. And also nitrous oxide is 5%. Notice over here, this vertical scale has greenhouse gas emissions in gigatons of carbon dioxide equivalents per year. Methane is a much more potent greenhouse gas than carbon dioxide, but there's a lot less of it in the atmosphere. So for the amount of methane we have in the atmosphere, it's the equivalent of 18% of all of the greenhouse gas emissions on the scale of how much carbon dioxide it would take. And then this last one here is the F gases, the fluorinated gases. These are basically man-made gases that are very powerful greenhouse gases. So what is the impact of all of these greenhouse gases on temperature, global temperature? So these are two records, global temperature change records from pre-industrial times. And again, the scale starts at 1850. The vertical axis is temperature anomaly. And what that means in this case is how much is the temperature different from what it was at 1850. So here you can see it's 0 in 1850. There's two records here. This red record is the Hadley Meteorological Center in the UK. And the yellow record is the Goddard Institute for Space Studies here in the United States. As you can see, the historical records are made up of different measurements from around the world, but you can see that while there are some differences over time, they pretty much follow each other with this low period here, a higher period here in the early 1900s. Starting in about 1970, these two records are pretty much in lockstep. That's when we started to have satellite measurements of temperature. So if we use the model, we can look at, this is the temperature change as predicted by the model. If we follow the baseline scenario, basically a change pretty much doing what we're already doing in terms of addressing climate change or trying to reduce our greenhouse gas emissions. So if the black is the baseline and the current scenario is the blue line, and currently, since we haven't implemented any solutions, they are the same. And by the year 2100, here on the right side, temperature increases will be 3.6 degrees Celsius higher than they were in 1850, or 6.5 degrees Fahrenheit. But as our climate goals are, as identified in the Paris Agreement, is we're trying to reach no more than 2 degrees Celsius by the year 2100 and striving for 1.5 degrees Celsius. So those are those two dotted lines here. So that might not seem like a lot, but it will have dire consequences. And so these are just some of the consequences of an increase of over 3 degrees Celsius in global temperatures. First of all, Arctic sea ice would be gone 2 out of every 3 summers. This has never happened in recorded history. The smallest amount of Arctic sea ice we've seen is in 2012, was about 2/3 of the ice was still there. Every summer it does recede from the Siberian coast, but always completely grows back. But to be completely gone 2 out of every 3 summers is a very, very dramatic change, and has large implications for the absorption of solar radiation in those regions, because you're moving from a bright white surface to a dark ocean surface, which would absorb a whole lot more energy. In addition, 50% of insect species would lose over 50% of their habitat range. This has dire consequences for agriculture because we depend on the insects to pollinate the plants so that we can grow our crops. So this has very serious consequences. Droughts would be predicted to be on the order of 11 months longer than the average length of a drought is today. And burn areas by summer wildfires in the Mediterranean would double compared to today. And we've heard year after year now, the past few years, the American West has had tremendous summer wildfires that have wreaked havoc in that region. And that just keeps getting worse and worse. Another aspect of climate change that would be impacted by this increase in temperature is sea level rise. So this is Boston today. Everybody here knows the Boston area. So this is Boston today. But if we have a 3.5 degrees Celsius warming, this would be Boston. All of these regions here, the airport would be completely underwater. This is a tool that you can explore on your own. Here is the link right here, but you see the previous slide, the global temperature rise was set to 0 compared to the present. And this is now set to 3.5. So it's a future sea level of an increase of 26 feet or 7.9 meters. Now, for those of you who are international, this is Amsterdam today. And Amsterdam with 3.5 degrees Celsius warming. You can see that most of Amsterdam would be underwater also. This is New York City today. So this is Manhattan, and this southern tip here, I'm just going to call your attention to the southern tip of Manhattan is where Wall Street is, and that will be relevant in a moment. This is the New Jersey shore, and Brooklyn and Queens here. If we have a 3.5 degrees warming, Celsius warming in New York, the Manhattan would be, all the coast of Manhattan would be underwater. You'd actually divide it into a couple of islands. The New Jersey shore would be mostly underwater, and Brooklyn and Queens would be underwater. Again, here is where Wall Street is. And so this is Wall Street on the ground today. And I'll call your attention to these two women who are walking by this window. You can see their heads are about halfway up the window. With a 4 degrees Celsius warming, the water level is up about 3/4 up the window, so that all of the people here would be underwater. So the area would be completely uninhabitable. This is London with 4 degrees of warming, and this is Parliament and the Thames River. The entire lower level of Parliament would be underwater. This is the Westminster Bridge, and the ends of the bridge would be completely underwater. So climate-related disasters have cost the world about $650 billion between 2016 and 2018. The damages associated with global warming, though, could total over $54 trillion by the time we just reach 1.5 degrees Celsius. So if we saw in that graph earlier, the temperatures have gone up a little bit over now 1 degree Celsius. So let's explore what we can do about this. So this is a screenshot of the model. And I'm going to point out a few things here. This is the net greenhouse gas emissions, and we have that baseline scenario and the current scenario. These are all of the different kinds of solutions that we can implement here, and we're going to explore these in a little bit more depth. But this is going to be the dashboard of solutions that we're going to try to implement, and we'll demonstrate those in a minute. But one of the things that I wanted to sort of orient you to is, what is the baseline? What are some of the things that go into the baseline? Notice here that some of the solutions involve population growth and economic growth. And so if we go here to what the baseline actually means, here we have that temperature rise over pre-industrial levels. And we have, you can see the 3.6 degrees Celsius by the year 2100. This is the baseline, assumes a population growth from about 7.95 billion people today to 10.9 billion people today. So if we move that lever and slow growth, there'll still be growth of population. It'll just be less than 10.9 billion people by the year 2100. And here is economic growth in the world gross product in trillions of dollars per year. And you can see that there's a tremendous growth there. So other level that we can do is either to decrease the level of growth, economic growth, or increase it or decrease it. And then these are the net greenhouse gas emissions. This is today in gigatons of CO2 equivalent per year, 57.6. And with business as usual, it is 93.74. So quite, not quite, but almost a doubling of CO2 emissions per year. So what are those mix of greenhouse gas emissions? So we have this, the carbon dioxide makes up 60 to 75, 70, 70, 76% of, a little over 3/4 of the greenhouse gas emissions that are going into the atmosphere now. So before we actually get to using the model, since this is an MIT alumni group, I wanted to give you a sense of how we know that the model is really telling us what we are hoping it will help us understand. So En-ROADS is designed to complement these large disaggregated models that take into account the science, the economics, and the social aspects to the problem. En-ROADS is a systems dynamics model. So any one solution or any one change impacts lots of different things. So these disaggregated models, or these really complex models, take a long time to run. Very much, the scope and detail is really high. This horizontal graph is speed, simplicity of use, and transparency. And so this En-ROADS model and C-ROADS is another kind of decision support model that used to do commitments of different nations on limiting their greenhouse gas emissions. These models are built to simulate what these large-scale disaggregated models actually show. And some of the examples of how you build confidence as models is you test the extreme conditions. Does a simulation robust in combinations of highest and lowest policy inputs in comparison to those more complex, detailed models? And what about the assumption sensitivity? Do insights change when those sensitivity parameters change? And in the models, you can change the sensitivity. I mean, it gives you the options to do that. And is the behavior reproducible? So if we look at historic behavior, does the model simulate what we already have been able to measure from the past? And so that we can have that confidence in future projections. And so these are just a couple of examples of the various models that were used and how as the baseline scenarios, and how the En-ROADS model performs in those different kinds of cases. So we have a history up here in which this is electricity generated by coal, and so this is from 1990 to 2015 in exajoules per year, an amount of energy per year. And you can see while the details are somewhat different, the general sense of how the En-ROADS model performs follows quite well. This one is the primary energy from coal, the baseline, how much energy comes from coal. And you can see that the En-ROADS model is right in the midst of all of those predictions. And then the primary energy from coal with a high price of carbon. And so the sense of the graph is also very similar. This model has also been used quite widely. So this is as of today. The En-ROADS model was released in December of 2019, and since then there have been almost 3,700 events like this one, and have involved almost 105,000 participants. So we're now going to explore this model a bit, and I'm going to first put in, I think I'm going to put into the chat where's the chat? Here. I'm going to put a link to a Google folder that, let me make sure that that's the right one. Okay, yes, this is the right one. Okay, so you'll go to that. I'll be referring to some of the documents in that folder. One of the things I wanted to point out to everybody is that when we get to the model, we're going to have the opportunity to look at different graphs. And I just wanted to give you an overview of some of the information, the depth of information that you can get from the model once you've implemented some of these solutions in the model. And so some of those drop-down menus will give you graphs of the impacts of your solutions on temperature rise, on sea level rise, and sea level flood risk maps. The air pollution from energy, that's basically a co-benefit of some of the solutions, so that it doesn't directly impact climate, but it impacts the environment and the quality of our environment. There's information about the decrease in crop yield based on the solutions that you input, and also ocean acidification. Then looking in another set of graphs on population and the GDP, you can look at the social costs of carbon, the reduction in the GDP versus the temperature increases, and the reduction in GDP from climate impacts, and also financially looking at the cost of energy. So I want to point out this graph. This is one of the documents that you have in that folder. It's the En-ROADS control panel. If you remember the pictures I've been showing you, these are all the different solutions that here in the middle that we're going to be able to implement. These bubbles then give you a sense of what that particular solution means. So for coal, if you move this slider to the left here, you're discouraging coal. If you move it to the right, you're encouraging the mining of coal and the burning of it in power plants. One solution that I want to point out, because it's a little bit different, is this new zero carbon solution. This is basically making the assumption that sometime in the future, but before the year 2100, a new source of energy is invented or discovered, and is very cheap and has zero carbon emissions. So that's another kind of solution. Then we have transportation. We can increase efficiency and electrification of transportations and building and industry. I've already mentioned growth of population growth and economic growth. We also have here land and industry emissions, which takes into those other greenhouse gases, the technological removal of carbon from the atmosphere, and then deforestation and afforestation. In addition to these solutions, we want to also consider how we can solve multiple problems at the same time, protecting the climate while improving the health and equity and well-being of society. So this is referred to as the flower framework. The flower here each has different petals. So if we look at the first petal here is health and well-being. Here are the red petal. Health and well-being and safety means improving the mental, physical, and spiritual well-being and creating safe conditions to live and work within. So is there solutions that we implement that would enable that to be more effective? Jobs and assets, providing meaningful work at a living wage and building assets in a community. Water and food, basically increasing access to healthy food and clean water, and food and water security. Resilience is building people's capacity to survive or even thrive in the face of disruption. Can some place that is impacted by some kind of disaster caused by climate change, can they rebuild? Can they survive that and move forward? Energy and mobility, bringing people secure access to energy and the ability to make things that they need and the ability to get around. And the last one is connection, leaving people more connected to each other and to the earth, which sustains them, opening up new opportunities for multi-solving. A second document in that folder gives you a sense for each of the different solutions that we will be able to implement, what might be the co-benefits for implementing that solution. For example, here for coal, taxing coal reduces air and water pollution and improves community and ecosystem health. If we have technological removal of carbon from the atmosphere, the growth of these nature-based carbon removal approaches like agricultural soil sequestration may help remove smallholder and farm profits. And then renewables is subsidizing, reduces air and water pollution, and also improves health and productivity, and also creates new jobs. So new jobs is another co-benefit of some of these solutions. The other table that you have is equity considerations. If you tax coal, you're making energy more expensive. And how can you really address that in the context of, how can you really address that in the context of people, vulnerable communities, which can't afford that the additional cost of energy? So now I want you to consider what actions you think of to help mitigate climate change, thinking about those different solutions that we have options of in the model. It could be actions that you take personally, actions that your organization that you work for takes, or your community takes, or that you think should take. The one thing you need to remember, though, is that when you implement that solution in the model, the assumption is that everybody in the entire world is implementing that solution. So take that into account as we think about this further, because we all know that it's not really feasible that every solution is going to be implemented everywhere equally around the world. Some solutions are more impactful in some places or more feasible in some places than in others. So, and also think about those near-term co-benefits from your proposal. How can you address more than one problem with one action? And in what ways could the implementation of that policy harm vulnerable communities, and how you might address that? So I want you now to type I'm going to take down the slides, and I want you to type into the chat what kinds of solutions we should implement here. And in this process, I'm going to show you how the model works. So think about what solutions we might try. Anybody want to type any suggestions in the chat? Carbon price, tax all carbon emissions, carbon price. So everybody's really big on carbon price. So we will implement that solution here. We'll implement what's called a high carbon price. Now, some of the things I want you to notice here, we're looking here at the global sources of primary energy, and this is the net greenhouse gas emissions. I can replay that change. So we've seen that it came down from 3.6 to 2.9 degrees Celsius. So that's a huge jump. And I can replay that change, and I want you to watch what changes over here in this global sources of primary energy. So I'm going to replay that change, and you can see that coal, oil, and gas come down significantly, as does bioenergy, and renewables goes up. And so I should point out here, the brown line for reference is coal. And when you are working with the model, you can mouse over it and it'll tell you what the amount of energy in exajoules per year is. And all of the graphs and En-ROADS go from 2000 to 2100. And so oil is the red line here. Dark blue is natural gas. The pink is bioenergy. The green is renewable energy. The light blue is nuclear energy, and new zero carbon is the orange. And right now that's zero because we've not implemented anything. You can see that the net greenhouse gas emissions go down immediately because we're implementing the carbon tax across all of the fossil fuels, coal, oil, and natural gas. Coal gets hit the most because it's the most carbon intensive of the fossil fuels, oil next and natural gas next. So any other suggestions? I know the chat went by me pretty quick. So anybody have any other suggestions? Energy efficiency. I see energy efficiency. Carbon capture and sequestration. So we'll try those two. We'll do energy efficiency. Let's try energy efficiency of buildings and industry. So we've gotten that down another 1/10 of a degree, and let's see what happens here. I'm going to replay that, and let's watch what happens over here. As you can see, all of the energy sources go down, and that's because you just need less energy. So we have a decrease in emissions there. And I'm going to do, I said I would do technological removal, so we'll increase that one. So that's medium growth, and that got it down another 2/10. So that's pretty good. But you'll notice that by removing carbon removals, it doesn't really impact input of carbon greenhouse gases into the atmosphere, because you're not impacting any of the sources of energy. So so I've been doing this at a pretty high level here. But I want to show you some of the depth of the model. And so we're going to go, basically, there's 3 dots to the right here of each of the different kinds of solutions. And so we're going to click on the 3 dots, and this brings up a much more nuanced ability to implement the solutions here. So here, as if we move the slider, we're just changing the taxing or subsidizing natural gas. But we can change the year that we start and stop that. We can just say that we're going to have a reduction in gas utilization and what year we're going to start that. The other thing we can do is we can stop building new gas infrastructure. And I'm going to implement that. And you can see what happens here is that the blue line goes down to 0 by 2100. We're going to stop building new gas infrastructure by the year 2025. And you can see this natural gas primary energy demand then goes down. It goes down slowly at first because the infrastructure is there and will continue to be there over time. But once the lifetime of many of these plants is on the order of 30 years. So after 30 years, if you're not building new infrastructure, then your use of natural gas goes to 0. We've gotten this down to 2.5 degrees Celsius. The other thing that I wanted to point out is that this little eye over here gives you even more information. So if we click the eye, you can see examples of these kinds of what examples of impacting the natural gas industry, the key dynamics, but you can also see those potential co-benefits of discouraging natural gas and the equity considerations of discouraging natural gas. And so these are areas where in the breakout rooms, I'm going to ask you to consider those changes as you pick the solutions you go to. And so I've shown you various ways that the model can be used. I also wanted to show you some of those impacts. So right now we've looked at, let's look at the impacts, and let's look at temperature change. And so you'll notice here that we've gotten the temperatures down to only 2.5 degrees C increase over the over pre-industrial levels. But pretty much there's not much of a divergence from the business as usual until about the 2035 or so. Okay, so that's the and also notice over here, while lots of things have gone down in this time period between 2020 and 2040, there's still a significant input of those gases in the atmosphere. Let's look at another impact. Now this is air pollution from energy. And notice that those impacts are immediate by reducing the amount by pricing carbon so that you're decreasing the amount of coal, oil, and natural gas, and by stopping building the new infrastructure for natural gas. You get an immediate impact on the particulate matter at 2.5 microns or smaller. This is the particulate matter that is regulated by the EPA. Okay, and let's see, we're going to go look at a few more. One other I want to show you is sea level rise. And this is another one that's very, very long term. The change doesn't actually, those changes don't really start to actually have any impact at all until after 2060. And then the impact is not all that tremendous. It's 1.15 meters globally by the year 2100 in business as usual, and 1.01 meters. So, basically 0.14 meters of change by the year 2100. And keep in mind that the clock doesn't stop here. We're just looking, we're using the year 2100 as a benchmark. Sea level will continue to rise just because the amount of energy in the system, there's a thermal inertia that slows down the actual manifestations of those impacts. So let's see if we want, let's see, let's take a look at the cost of energy. There's the cost of energy. So we've increased the cost of energy. So there's tremendously from about $24 per gigajoule to something on the order of $33 per gigajoule. So a significant increase in the price of energy that really doesn't come down over time. So let's go back to this. Okay, so what we're going to do now is we're going to go into breakout rooms. Let me pull up my slide again. I want to show you this in a second. Okay, so in breakout rooms, and I think we're going to probably have on the order of 6 breakout rooms. You're going to work together. I'm going to give you a link to the model as it is now with the solutions that we've implemented thus far. I'll put that in the chat after I also put these instructions in the chat. And you're going to experiment with different solutions, choosing one at a time, and seeing where you can get the biggest bang for the buck. Which one solution, choose your top solution by testing these ideas in the En-ROADS model. So you test one and then you put that back to the baseline case, and then you test another one and see which one you can gives you the biggest change in temperature. I also want you to identify those co-benefits and equity considerations for your solutions. Note that you are not trying to get to 2.0 degrees Celsius by 2100 in the breakout room. We're going to collectively try to get to that goal. And then I want you to choose a spokesperson for your group to report out. So you do need to remember your group number, because I'll call out for the spokesperson by group number, to offer your groups one solution to be implemented at En-ROADS. And I suggest that you identify a backup solution too, in case somebody else, some other group before you picks the solution that you've picked. And then describe the reasons for that solution and describe the co-benefits and the equity considerations for that solution. So I'm going to put those, because we're going to, once you go into breakout rooms, you're going to lose the slide. I'm going to put those instructions here in the chat. And then I'm going to go back to the model. And I can share the scenario here. You can share it various ways. I'm going to copy the scenario link, and I'm going to put that in the chat. Okay, I'm going to have to put the instructions in the chat again. Okay, does everybody have the link now and the instructions? Well, I'm not hearing anything, but everybody's on mute, so hopefully, if somebody didn't get them, then, okay, great, I see them. All right, great. Okay, so we are ready to go into breakout rooms. Okay, welcome back, everyone. I dropped in, I think, on everybody's breakout room. I'm now going to call on the spokesperson from each group, so you can offer your solution and we'll implement it here in the model. This is the model as it was when we went into our breakout room. So room 1, who is your spokesperson and what is your what's your solution that you would offer?
Wait, are we room 1?
Room 1 was Anna Morrow, Bob Gilbert.
That's not us.
And
Okay.
Nancy Stevens. So which of you, Anna, Bob, or Nancy, do you want to report out?
We were talking about the carbon pricing, but if that's already included in the model, then we would put it higher. Actually, we'd probably double it. And
Well, let's try it. What other solution would you do? Let's try something in addition to carbon pricing.
okay, so the next thing was, I think, was electrification, building
Electrification of which? Transport or building?
Oh, building electrification.
Building electrification. Okay. So it didn't have much impact on the temperatures at all. Let's replay that. And you can see that there's very little impact on the global sources of primary energy also.
Having done that for about 40 years, building systems, that is a silly thing. So anyway.
That's a silly thing. You want to explain that?
Well, I've been that's a thing that's going on a lot in Boston. And what it is that people are saying, oh, I don't want to use natural gas, or I don't want to use central steam. I'm going to use electricity because electricity doesn't have any impact. And unless God has started delivering electricity to us, all the electricity that I know has to follow the EPA criteria. And as I might have mentioned, I don't know if it's in the breakout, but basically a ground source heat pump in most situations has a bigger CO2 impact than burning natural gas. So unfortunately, electrification is actually counterproductive.
Okay, well, thank you. So let's go on now to breakout room 2. Gabrielle, Gerald, Jeff, Jose, and Tim. Somebody from breakout room 2 want to offer their solution?
Sorry, I was muted. Sorry. We went through a couple of trials, and we concluded something that violated your rule, which was we found out very quickly that we needed to have a combination of solutions to have a serious impact. Nevertheless, after we tried a few things, we came up with a consensus of the first strategy, our primary strategy that is different from what you have in the base case, was to go a lot more heavy on the removal of methane from land emissions. Literally, in other words, agricultural emissions to be removed as much as possible. And therefore,
Okay,
trying
so
to...
here's this methane, and we can actually go into the detailed settings, and here's agricultural emissions. And I think we have to put a negative. So I'm going to put a minus 100% here.
We just moved the macro scale to the left.
Yeah, but that doesn't focus on agriculture alone. That does both energy and industry emissions. You said you wanted to do agriculture, so
We said land-based. We went under the land-based category. So yes.
So you want to, so you don't want to do it just, all right, so we'll take this.
We can
away.
do it. I think it's more impactful if you do everything rather than just agriculture.
Okay. All right,
assuming-
so there we are we came down from 2.5, I think it was 2.3. Notice here it has very little impact on the amount of greenhouse gases that are put into the atmosphere.
Okay. And our backup.
This is not the amount of greenhouse gases. This is the amount of energy from primary energy sources. So it has very little impact on that. But let's replay that again. And you can see that it has the impact on greenhouse gas emissions really occurs mostly after the year 2060. Okay, and
Our
did you think
backup
about
was
the equity considerations or co-benefits?
Yeah, again, the co-benefit would be a healthier lifestyle because you're doing more protein, plant-based protein food, more Impossible Burgers, Beyond Meat and all that. So you have health benefits and therefore lower costs to a lot of people that are having high healthcare costs. That's one. The other one that we had as a support or as a backup, if you want to call it that, we went 100% electrification for both transport and buildings and industry.
Okay, well, we'll get to additional solutions after everybody gets a chance to offer theirs. So I'm
Okay.
gonna leave you with just the one for right now. Okay, breakout room 3, Bill, John, and Mike.
Yeah, I'm the spokesman, and surprise, surprise, 100% electrification of transportation. But we did transportation and buildings and industry. So that it was
All
really
right, so
the
you have to pick one.
well,
It's
okay,
not how it works.
we'll do transportation then. Since
Okay, well,
somebody
'cause
else
we already
already
have some for in buildings and industry.
yeah. Okay.
And so let's replay that. It didn't impact temperature very much.
Well, no, that
um,
was we moved that all the way to the right.
Yep.
That was 100% electrification.
Oh, that's
There you go.
Highly incentivized.
That's right.
okay. How politically feasible is that?
Well, it depends on, it's feasible if, people realize the problem. I mean, you have to move the temperature down. So that was the,
Okay. And what are the equity considerations and co-benefits?
well, you have cleaner air, obviously. You have economic development with this if you do it right.
Okay. Very good. Well, what all of you discovered in your breakout rooms was what the whole point was supposed to be when we came back together was there's no one solution. So let's go on to breakout room 5. Ron, Shai, and Tom, and William.
Oh, okay. Well, we cheated. We know how to run the system. So we knew that carbon price was the big winner, but that's not what. So we wanted to do two things. We wanted to push the carbon removal technology way past the right end of the slider bar and put it at 300% of what it's allowed to be. So we thought that that would be a good thing. And some of the people advocated that, yeah, they thought it was actually possible to do that. So that was kind of our innovation number one. And then innovation number two, which isn't going to show up on here at all, was to do hydrogen technology, basically through various.
That's a new zero carbon technology.
Well, okay, fair enough. Yeah.
Yeah, but you've got it set so you can set it anywhere between 0 and 2.
Yeah, well, that's one new technology and a second new technology.
That's not the way we do quantitative analysis in math.
Well, the model is transparent. You can, I don't know what the equations are, but you can look into what the equations are and how they actually develop that scenario. Okay, but we added that, and while basically by adding this new technology, basically it impacted renewables and they came way down. Not much else changed and the temperature didn't change at all. So basically you traded one thing for another that both are zero carbon.
Now, wait a minute. You didn't give us credit for our number one thing, which was the carbon.
No, but you only get one.
Well, the first one I said was carbon removal. So let's go with that. At least we get some score.
All right, but I can't make it go past the end of the scale. That's what you told me.
But you could make it go to the end.
Yeah, but that's not what you said. Okay,
Well.
I think go to the end. All right, so we get to 1.8. All right.
There you go.
All right, so now we need to continue to try and get even further. So we want to get to 1.5. What else should we try besides sliding something all the way to the end?
How about more energy efficiency in the transportation?
Energy efficiency brings these energy use down, but doesn't really impact greenhouse gas concentration all that much. One of the things to notice here is that oil is still really high out in the 2020s, out past 2030. And when you put that carbon in the atmosphere, 20% of it's still there in 1,000 years. And so one strategy would be to try to eliminate the coal and the oil earlier. See, these these are the ones that are now, because you've gotten them all way, way down as you get out into the century. This is where things are still high. So want to try something else?
Yeah, Tom and I were big on nuclear, but again, we can't set it to a high enough value.
All right, so let's try, well, but with the things, if we,
See, that nuclear is a way for you to
even
get
if you make nuclear
electricity
go way, way up,
without
you're
CO2.
still not impacting the amount of carbon dioxide that's being put into the atmosphere by these fossil fuels.
So why don't you take away the supply?
Okay, so that's what I was
Coal-
going to suggest.
Coal and oil.
Why don't we go down and stop building new infrastructure in 2025?
Yeah.
Okay, so that only gets us down another 1/10 of a degree. And we've got oil going down to zero. It's still high up here. So another thing we could potentially do is reduce the utilization of oil. So I'm going to do minus 50% here and see what that does. And wait, not 500.
Minus 500.
50%.
Tried that.
And let's see, if we do the year 2022, oh, I have to enter, okay, I have to, it's not minus, it has to be 50%. All right, it still did not change that temperature very much. It changed the amount of oil, but still.
Well, so in room 5, we did have a secret solution, which was to get in the Wayback Machine and go back and kill John Rockefeller.
What other things have we not even tried yet? How about slowing population growth?
Yeah, well,
No, we talked about that and decided that was not, who are we going to talk to? So,
What?
Actually stopping coal earlier too impacted. It was quite an impact because coal is so,
Okay, so we can stop building new coal infrastructure?
yep,
yeah, that'd be nice.
Yeah.
that should be the first one, not oil. Coal should stop.
Yep.
Coal should stop, but I always find that oil is really, oil is still pretty high up here. It's higher than coal. So
True.
we've tried to bring all of these down. So we have bioenergy and so what else? So let's just see the impacts on other things. Let's see, impact on sea level rise. So sea level rise is already still baked into the system. So before we came out with, when we had it down to 2.5, sea level rise by 2100 was going to be basically, I think 0.99 meters, and now it's 0.89 meters. So we brought it down a little tiny bit. Let's look at financial, the cost of energy. Cost of energy, so now we still get that tremendous increase in the 2030s to 2040s, but this time it's come down a bit as we get further out. So that's good. And let's see, impacts on decrease in crop yields from, so the black is the baseline. That's when we had the 3.6, maize crops would be down 21%. Now they're only with 1.6, they're only down 6%. Wheat was down 17%, is now only 5%. And rice was down 9%, is now only 3%. So we're getting better.
Could I ask a question about that? Why do we assume that crop size, not really just yield, but is going to go down? Because huge areas of land are going to become arable now in Russia and northern China and Canada and places like that. I mean, crop yields might go up with higher temperature.
Overall, globally, it has been using those very complex models, which take into account those regional differences, still come out. I mean, basically, in the United States, supposedly the breadbasket of the United States moves up into Canada. But still, overall, the model predicts that crop yields will come down. So I wouldn't call it an assumption. There's assumptions within the model, that's true, and we can dig into that in more depth if you're interested in looking at those equations.
Aren't you losing some land because of sea rise?
You're losing land because of sea level rise. Yes, that's true too.
Right.
Let's look at that. One of the other impacts is
That's
sea
generally
level rise
not
covers
arable land.
mass.
It's People are at the coast.
Oh, I see what you're saying. The coastlines do not have arable line.
Yep.
That's reasonable.
Yeah, that's true. So I'm gonna put Boston in here. Just so that you can see what this, what this can do. So what this model, what this is showing you is that by bringing the temperatures down from an increase of 3.6 to 1.6, the land at risk, that's still at risk, is in the blue, but the land saved by the actions we've implemented is in the green. And let's zoom in a little bit so that you can see that a little bit more clearly. So this kind of shows you the impact of your solutions on sea level rise, but you're right, this won't affect agriculture very much.
No, you bring up someplace like Chicago or Montreal, and you'll see that there's not much loss of arable land.
But even places in Asia, like Indonesia, for example, where you have a lot of rice paddies, etc.
Hopefully that's in the model. Is it? Anyway.
Yeah, with sea level rise, you'll have more saltwater intrusion further inland.
So you can see, you can see the small, as you zoom in, you can see the impacts.
Not big.
Not large, no.
Right. So how do we get rid of that hump, the short-term hump?
This one here,
Well, no. In
cost of
the,
energy or
in the
the
in the supply.
energy.
Where we had oil basically very strong still in 20.
Yeah, this
20
one.
Yep, this little hump there
All
between
right, let's
2020 and
see.
2030. How do we get rid of that?
Well, with 2022 right now,
Right.
you know, I mean, let's
I'll-
get practical about it. I mean,
Can't
I
do it.
understand the model, but the fact is how to get, you can't change it that much realistically between now and 2030.
Yep.
That
It's
is
going
that's
down.
the point here. So what I did now is I changed this from 50% to 100%. And so this comes straight down. It takes a while. It doesn't get to zero until 2032. As John suggested, it just takes them, it's 2031, it gets to zero.
And you got a half a
2030 is
degree
zero.
centigrade.
Say that again?
Half a degree centigrade.
Yeah, it did get down another half a
Yep.
degree centigrade.
Well, but it's still
Well,
not.
but that's also an extreme to go down 100%. I mean,
Right, that's an extreme.
What do all the people do with gasoline-powered cars?
Right. And a few major oil companies that have refineries, et cetera.
Well, actually, so if we, let's see if I did look at this. So electrification of cars, and if we look at these related graphs, let's see. Electric share of total capital and transport. And so you can see that there's still some, either it's 85%. If you implement the solutions which we had which we did here, which was electrification of new transport for road and rail.
Right.
There actually we didn't do anything for air and water. So that came out to be, by 2100, it's 85% of all transportation is electrified by the year, and it actually gets really close. It gets up to that rather rapidly. By 2035, it's pretty much there. Let's see what happens if we do the same thing to, what is it, 98%? Let's do the same thing for.
Well, I don't know about the air part, but the water is conceivable.
So air and water, so now it's 97%. So that was the extra
Extra boost.
12% there.
I noticed that when you turn up the electrification, what goes up as far as the source goes is renewables, even though the renewables thing doesn't move.
Renewables goes up some.
Well, the renewables goes up a lot. No, just go over down there and slide the, I've got it running here offline. Take the electrification on transport and slide it up and down from 0 to 100%. And you can see that that's assuming that all the electricity for the electrification is coming from renewables.
Hmm.
But yet, but the renewable slider stays right where it is.
That's interesting.
So if we've implemented these numbers inside here. So if I make these go back to 0 and then implement the sliders, I think that was the problem here. So if we go back to this, and now you're saying that this didn't have any impact. Well, because that's the reason this doesn't have any impact on renewables, I think, is because we've implemented all of these other things.
No, it does. Well, maybe it does. I'm just sliding electrification on transport from all far left to far right, and it goes to far right. The things that go up are nuclear and renewable.
All right. So one of the things that is a takeaway from this is that that it's a systems dynamics model, but we have other solutions that are implemented. It impacts how large the impact can be on of another solution. So if we were to take everything away and just change electrification, if we can even do that. Here, let's try this. I'm going to pull up another clean version of this model. Okay, and now with nothing else implemented, well, it's harder to see. I like to use the line graphs rather than the wedges, but let's just try moving that. So all those changes occur when you haven't implemented any other changes. And look at that oil line come down. But when we did so much to oil before to bring it down to 0, we stopped building oil infrastructure. We reduced oil utilization by 100%. Electrifying cars didn't make any more difference because you weren't using oil to do it.
Hmm.
Okay,
But
well,
we started getting more things from renewables just because we electrified the cars.
okay, so we are really at the end of our time here. So I did want to, we're going to skip a lot of my last slides. I think most of you are familiar with it, but I did want to make one more pitch here. The question is what people can do. And this is something that you can share with others. I especially do this with student groups where a lot of their focus is on the individual and the local. And the individual and the local are very important because it helps build a mindset of society. You're influencing other people so that by your actions and the actions of your community and groups like this, we impact our social networks and our organizations. And one that I want to point out specifically is this public creating laws, organizing and voting. And I am a number of people on this call are part of the MIT's Alumni Energy Environment and Sustainability Network. And we're doing efforts around education, which this is one, but also around advocacy. And so we have created, we've done a number of letters to legislators. And what we're asking is to promote different kinds of solutions. And each one is focused on a different kinds of solution. So we have one in specific now that we are asking alumni if they agree with it to sign on to. And that is for the electrification of the postal vehicles for the post office. And so I'm going to put the link to this in the chat. And what this is a link to the letter that this group has put together. And we're seeking at the top of the letter is a link if you're interested to sign on and we send the letters to everybody who signs on. We identify their senators and congressmen, and the letter gets sent to all of the congressmen and legislators from a group of MIT alums who are their constituents. Okay, so we are past our time. So I want to say thank you. I enjoyed the conversation we had this night. I hope you found it interesting, and you can visit climateinteractive.org to learn more about this model. It does provide a in-depth, you can look at the equations and the assumptions that are made in the model, and you can change them. Thank you very much. And there's my contact information if you have any other further questions.
Thank you, Tamara. It's like, I'm sure it was a feeling of like herding cats.
Yes, well, I know MIT alums are very smart people who have very, very strong opinions and are interested in pursuing conversations in various directions. So I appreciated the variety of conversations.
Well, thank you again.
All right, Tamara, thanks a lot.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.